Welcome back to week 6 of the course. So we are heading into the last 2 weeks of the course now. Hang in there, you've almost had it. So let's dive straight into the topics for today. As always, I'll start with a recap. So I'll start with discussing what we have learned so far about linear multiple regression analysis. And then we'll introduce 2 new topics. And both of those are about dealing with categorical variables in regression models. So first we'll discuss how to deal with categorical X variables or categorical predictive variables, if you want to call them like that. And the way to do that is to use something called dummy coding. So we'll discuss how dummy coding works and how to interpret regression models where we have dummy coded categorical variables or X variables that are categorical. So that's going to be the first part of this video lecture. The second part of the video lecture, we are going to take some first gentle steps into how can we analyze categorical dependent variables. So Y variables that are categorical, which for a political scientist is quite often very useful because lots of the things that we want to explain are basically categorical outcomes. Yeah, so we'll make a start of discussing that. There's quite a couple of things that you need to know before we can really look into the technicalities of doing that in regression models. So the last week of the course is going to be entirely devoted to that, but it's important that we first get the basics down so you will be able to follow along next week. So that's what we'll close off on. So again, starting with a little bit of a recap, what do we know now? Well, we know how to use linear multiple regression analysis. We know how to technically execute that. We know how to interpret it. We know how to do various statistical tests. And we know that in general, why are linear multiple regression models awesome? Well, because they give us these linear effects of x's on y's, where we can control or adjust for differences on other variables in our cases by including those variables in our models. Yeah, so for instance, if you want to say something about a causal effect and you think, well, there's a potential confounding variable, well, if you can observe that confounding variable, you can include it in your regression model and adjust for it, and so you get better estimates of the true causal effect of x's on y's. So far, having assumed that those x's and y's are continuous because we estimated linear effects, and that of course only makes sense if we in fact are talking about continuous variables. And why is that so awesome? Well, lots of the theories, maybe even all of the theories, either explicitly or at least implicitly, that we want to test, that we want to use to explain the world, will tend to make statements about causality, about causal mechanisms, about how things lead to other things. And that means that if we want to really critically evaluate those theories, it's of course great if we have methods that allow us to get closer to those causal effects that are implied by the causal mechanisms. Yeah, and so multiple linear regression model is for that reason a much used tool, not just in our field, but in many fields of science. Yeah, so this is what we learned. We also learned how to extend those linear multiple regression models in various ways that can be theoretically super interesting. For instance, we already saw that even though it's called a linear multiple regression model, we can actually use it to model non-linear effects of our x's on our y, of our x variables on our dependent variables, by adding polynomials to our model, which of course can also be great. Well, if your theory predicts a nonlinear effect, of course you want to have a method that allows you to actually analyze a nonlinear effect, and this is one way of doing that in regression models, that we can include the polynomials of our x variables. Yeah, so for instance, if we were expect based on our theory that there should be actually a curvilinear effect, so it's like going up and then going down again, or the other way around, going down and then up again, then we can do that by including our x variable to the power as 2 as a second independent variable in our model, and then we get an estimate of the nonlinear, the curvilinear effect of x and y. So that's great because often, or at least sometimes, theories aren't just about linear effects, they are sometimes about nonlinear effects, so it's great if our methods fit with such non-linear effects. The other way we can extend linear regression models that we learned about is that we can do a so-called mediation analysis, where we are trying to disentangle direct and indirect effects of our x variables, of our independent variables on our dependent variable. And again, that can often be super theoretically interesting, because what are we doing then? We are saying, well, to what extent can we explain the effect that x has on y, that our independent variable has on our dependent variable, through that effect that x has on some third z variable. Because often always our theories won't just tell us that x has an effect on y, but ideally our theories will tell us why x has an effect on y. Why does our independent variable have an effect on our dependent variable? So that is the causal mechanism. And sometimes we can observe parts of that causal mechanism to figure out, well, okay, our theory doesn't just say x has an effect on y, but it also says why that effect exists. Let's check whether that's also the case. Again, this gives us more room to really critically evaluate and potentially falsify our theoretical ideas of how the world works. This mediation analysis is a great way of getting a bit further in critically testing our theories. Another way we can extend regression models that we learned about is a so-called interaction analysis, also referred to as a moderation analysis, where we're looking at the conditional effects of x on y. So not just, well, what is the effect of our independent variable on our dependent variable, but going further and looking at, well, what does that depend on? Is that maybe different for different people? And if yes, why? How so? So that's the idea of having conditional effects, and that's what we learned we can do with moderation analysis, which is of course great, again, for theoretical reasons, because we have lots and lots of different theories in the social sciences. Some might argue we have way too many theories in the social sciences. And if we just look long and hard enough, there's probably always going to be some empirical observations that fit with our theories. So the really interesting questions are often about, well, when do these theories work? In what kinds of situations, for what kind of people, for what kind of countries do the causal mechanisms that are implied by our theories, when do those causal mechanisms operate? So that again gives us much more room to test our theories by looking not just what does our theory predict about the effect of x and y, but also what does our theory predict about what that effect itself then depends on, what it is should be conditional on. Again, giving us more room to potentially falsify our theories. And more in general, one of the answers that social scientists will often give you if you ask them about, well, what is the effect of something on something else, will be, well, it depends. Well, now that you have learned about interaction analysis, you can ask the follow-up question. That's great. What does it depend on? And have you analyzed that through some kind of moderation analysis? That's of course always great to be able to critically engage with those kinds of statements. So lots of ways we can, 3 different ways in which we can extend the linear regression model to do even more interesting theory-driven research. So if you look at that, we learned a lot already in the 5 weeks that we've had this course now. We really covered a lot of ground and really have become much more aware, hopefully, on how can we not just look at regression coefficients and say something about p-values, but really use those methods to do interesting stuff theoretically, to really critically engage with our theories. Now, there's a couple of things we still really need to discuss. And one thing that we really need to discuss, and so far we haven't yet, is, well, okay, great. That's assuming that we have a continuous x variable or x variables and a continuous y variable. What if that's not the case? Because quite often your hypotheses will be about x variables, for instance, that are not really strictly continuous, or maybe not continuous at all. Variables that are really categorical, where there's different categories, but it's really not like we can just straightforward say what is a continuous variable. How do we deal with that? Because that's a lot of the things that we might be interested in. For instance, what are the effects of gender or socioeconomic status or employment status or party membership? What are the effects of those on our dependent variables? If you think about something like party membership, well, people belong to different political parties, but it's not like we can just say, well, this person belongs to this party, so that's a 2, and then that person belongs to another political party, so that's a 3, and this person belongs yet to another political party, so that's a 7, and have some kind of meaningful scale of different numbers, right? So how can we deal with that? Well, thankfully we can. We can include such categorical X variables into our regression models. We just need to use a trick, and that trick is creating dummy variables. So dummy variables, it has nothing to do with being a dummy or being stupid. It is basically a trick that we use to create variables that are going to be substituting for our categories. So being dummies for our categories. So how does that work? Well, as always, let's start with abstractly what's behind it and how does it work technically, and then we'll go into concrete applications. So one thing that's important to be aware of is that this works if your categorical variables are mutually exclusive. So meaning that if you have a variable that is measuring things in categories, then your cases can only belong to one of those categories. Yeah, so if we say, for instance, we are looking at socioeconomic status and say, well, it's basically a categorical variable, or at best an ordinal variable, but there's just different categories. It's not like we have just a scale running from minus infinity to positive infinity or something, but let's assume that we have measured socioeconomic status in 3 categories: low, middle, and high. So we have people with low socioeconomic status, middle socioeconomic status, and high socioeconomic status. Then if we talk about these categories being mutually exclusive, that means that each person that we observe can only belong to one of those categories. Yeah, so if you belong to the low category, you cannot at the same time also belong to the middle or the high categories. If you belong to the middle category, you cannot at the same time also belong to the low or the high category. If you belong to the high category, you cannot belong to this at the same time also to the middle or low category. So these categories have to be mutually exclusive. All of our cases can only belong to one of the categories that we are considering with our categorical variables. They also, these categories need to also be coded in such a way that the categories are exhaustive, meaning that if we consider all of the categories that we have measured, then we should be able to cover all of the cases. Yeah, so if we say we can reduce the variable socioeconomic status to 3 categories, middle, low, and high, then being exhaustive, these categories being exhaustive means that all of our cases should either be low, middle, or high. So all of our cases need to fall within one of those categories. Okay, so how do we do dummy coding? Well, first things is we need to consider, well, how many categories are there on our categorical variables? How many categories are we dividing our cases into? Are we saying, well, our categorical variable is whether or not people have cats, then we are dividing people into 2 categories. Are we saying we are dividing countries into being new democracies or old democracies or non-democracies, then we are dividing countries into 3 categories. If we say we have party membership and we have 14 different parties in our party system, and we want to make a variable that covers these categories for party membership for individuals within that party system, then that means that there are at least 14 different categories for the 14 different parties, and maybe even a 15th category for allowing for people to be not member of any of the political parties. So the first thing we need to consider is how many categories are there. And then we can start creating these dummy variables, and the number of dummy variables that we need is going to be the total number of categories that we have minus 1. So if your variable is measured in 2 categories, that means that we need to create 1 dummy variable. If we say well, we have 3 categories, then we need to create 2 dummy variables, 2 dummies that we are going to use for analysis. If there are 4 categories, then we need to create 3 dummy variables or dummies, etc., etc. Which means that there is always 1 less dummies than there are categories. And that 1 category for which we are not creating a dummy variable, we will call that the reference category. Why k-1? Why do we need 1 dummy less than we have categories? Well, this goes back to we assume that our categories are mutually exclusive and exhaustive. And if our categories are mutually exclusive and exhaustive, that means that all the information that we can have regarding to which category our cases belong is already contained in information of the membership of our cases to the total number of categories minus 1, because they are mutually exclusive and exhaustive. Yeah, so for instance, if we say, well, we have socioeconomic status in 3 categories, and those categories are mutually exclusive and exhaustive, then if we know which cases belong to the middle category, and we know which cases belong to the high category, then we don't need to worry more about the other cases, because we know by definition they need to belong to the low category, because that's the only one we have left. So if you're not high and if you're not middle, logically you can only be in the low category. So how do we create these dummy variables? What we're going to do is, for each of our cases, we are going to create a dummy variable, and cases that belong to the category that this dummy variable is supposed to capture, and we're going to give them the value 1. And the cases that do not belong to that particular category, we will give them the value 0. Yeah, so let's start with a super simple example, and I'm going to do one that's a bit controversial, because the European Social Survey still codes gender into 2 categories, which of course you might think about, is that still a good thing to do normatively, but also from a scientific standpoint. If you want to have a discussion about that, I'm always open to that in one of the Zoom meetings. But for now, well, the European Social Survey still codes gender as male or female. So we can assume, well, that there are 2 categories that are mutually exclusive, and at least that's what we're assuming then, exhaustive categories. The nice thing about that, at least it makes it for a very simple example, because now there's only 2 categories that we need to worry about. So that means that we have 2 categories. We're going to have to create 1 dummy variable for one of those categories, and the other category is going to become our reference category. So we need to choose which one of these are we going to pick as the reference category, and I'm just picked male here. We could have also picked female, it really doesn't matter. So in this case, let's just go with male as the reference category. So we have 2 categories, we are picking male as the reference category. That means we need to create 1 dummy variable in our data set, where for each case that we observe, we're going to look at that case. Well, is that case female or is it male? And if the case is female, then we're going to assign the value 1 on that dummy variable to that case. If the case is male, we are going to assign the value 0 to that case. So now we created a dummy variable for gender for all of our cases, where all the people that indicated female on the questionnaire got the value 1, and all the people that indicated male on the questionnaire get the value 0 on this 1 dummy variable. Let's pick a bit more of a somewhat more complicated example. Let's consider religion. Now let's say we are analyzing a religious denomination in the Netherlands, and we created the following 4 categories. None, so we are allowing there some people to be non-religious. Catholic, because that's one of the most dominant religious denominations in the Netherlands still. Protestant, because that's one of the other most dominant religious denominations. And we also create another category, other. So we wind up with a total of 4 categories. Well, why other? Well, because not everybody that's religious, belonging to a religious denomination in the Netherlands, belongs to either Catholic or Protestants. There are lots of other religious denominations that people may belong to, some quite large, some really small. And again, our categories have to be not just mutually exclusive, but also exhaustive. So somehow we need to also create a category for all these other different religious denominations. So in this case, I'm using other for everything that's not Protestant or Catholic, because if you look at the distribution of people around different denominations, then you will find that for all the other religious denominations, the number of observations that we have in a sample of, in this case, 1,600 people is so small that it's really not possible anymore to really analyze differences between those smaller religious denominations. But we still need to somehow cover those cases, so we can assign the category other to those remaining religious denominations. So now we have a categorical variable with 4 different variables. So stop and think, how many dummy variables do we need? Well, we need 3 dummy variables because one of those categories we have to choose as the reference category. And again, it's arbitrary which one of those you choose. So in this case, I've chosen none as the reference category. So that means none is going to be our reference category, and we need to create 3 dummy variables. One dummy variable for the Catholics, meaning that we are going to create a new variable in our data set. We are going to call that the Catholic dummy. And then for each case, we're going to look at, is this person belonging to a Catholic denomination or not? And if the person is belonging to a Catholic denomination, we will give that case the value 1 on our dummy variable. And for all the other people, so the people that are not religious, or the people that belong to a Protestant denomination, or the people that belong to other religious denominations, all of those other people will get the value 0. So that's our first dummy variable. Then we're going to create a second dummy variable for the Protestants. So this is going to be the dummy variable that captures whether or not people are member of a Protestant denomination. So again, we're going to create another new dummy variable in our data set. And for each case, we're going to look at, is this person a Protestant? Then that person gets the value 1. And all the other persons, so the people that are not religious, or the people that are Catholic, or the people that belong to other religious denominations, all of those get the value 0 on our dummy variable for Protestant. And then we do the same thing with the other religious denomination dummy. Again, we're going to create this third new dummy variable, other, where for each person in our data set that belongs to a religious denomination that's neither Catholic nor Protestant, but something else, that person will get the value 1 on that dummy variable, and all the other persons, all the other cases in our data set get the value 0. So the people that don't belong to any religious denominations, the Catholics and the Protestants, they all get the value 0. So that's how we create those dummy variables. And yeah, again, we have to pick as a researcher one of those categories to act as the reference category, and for that category we are not creating a dummy variable. So let's look at, well, if we talk about hypotheses, if we think about independent, these categorical variables as independent variables, how would we formulate this hypothesis? Well, the important thing is that if we are talking about hypotheses about effects of dummy variables, then we need to be clear in our hypothesis about which reference category we are using. So it's really important that if you formulate such hypotheses that you include clearly your hypothesis, how the categories that you cover with your dummy variables differ from those that are covered by the reference category. So for instance, we picked male as the reference category for the gender variable, and let's assume that we want to test the effect of gender on trust in parliament. Then because we have an hypothesis about that, for instance, maybe so our theory predicts that some argumentation that maybe women don't feel as well represented than men, and therefore are less trusting of parliament. Then if you want to test that theory, we would want to estimate the effect of gender on trust in parliament. And given that we've picked men for our dummy coding as the reference category and created a dummy variable for female, for women, then our hypothesis would need to make clear what difference we are expecting. So in this case, we would say women have less trust in parliament than men. Men, because men in this case act as the reference category. If I would have picked women as the reference category, it would have been the other way around, and we would have to say men have more trust in parliament than women, assuming the same theory. And for our religious denomination example, again, we have to make clear in our hypothesis what we think about the difference between those categories for which we created dummy variables relative to the reference category. So for instance, if we theoretically expect that maybe Catholics are, better represented in parliament, and therefore Catholics will be more trusting of parliament, then we need to make clear in our hypothesis and how we formulate that this is about the difference between Catholics and our reference category. So in this case, we picked the non-religious people as the reference category. So we formulate our hypothesis as Catholics have more trust in parliament than non-religious people. We could do the same thing for Protestants. Again, Protestants have more trust in Parliament than, again, our reference category, the non-religious people. Or we could even say people in general that are religious have more trust in Parliament than non-religious people, and then just in our analysis split those religious people out into Catholics, Protestants, and others. But again, we always have to make it clear in our hypothesis, well, compared to what? Because we are now comparing different categories, so we need to make clear in our hypothesis what are we comparing with what. And this then also tells you, well, how do you pick reference categories? Well, that's based on primarily your theory. What exactly is the difference that you expect between the different categories? And then based on that, you pick one of those categories to be the reference category. Yeah, so that's how you get your reference categories. So let's look into a more concrete example. And again, we're going to start super simple. Let's just assume that I want to analyze this hypothesis that women have less trust in Parliament than men. And I'm not worrying about any kind of control variables or other variables yet. So I'm looking at a super simple regression model where I'm just taking trust in Parliament as dependent variable and the gender as the independent variable. And what did we do with gender? We created this dummy variable for female. Yeah, remember, we created a new variable in our data set where everybody that is a woman indicated 1, and everybody that is a man on the questionnaire indicated a 0. So now we get this dummy coefficient for female because we picked men as the reference category. So we could estimate this regression model with our dummy variable. And then if we interpret this regression model, as always, we do that in terms of predicted values. Well, what would be the predicted value for women? Well, it would be B0, our regression constant, our intercept value, because that's the same for everybody. That's the starting point. Plus the regression coefficient we get for our female dummy multiplied by 1, because how did we code the variable? We gave every case that is a woman the value 1. Yeah, so we are multiplying the coefficient by 1, what would be the predicted value for men? Well, again, it would be B0, our constant in the regression equation, plus, again, that same regression coefficient for the female dummy multiplied by 0, because we gave all the people that indicated male on the questionnaire the value 0. In other words, works out to just 0. Yeah, so the predicted value for men in this case is simply the constant. Again, we can do this for the somewhat more complicated example with more than one category. So let's look at what is the effect of religious denomination on trust in Parliament. Well, we distinguished 4 different categories: no religious domination, Catholic, Protestants, and others. We picked no religious denomination as the reference category, so we don't have a dummy variable for that category, but we do have a dummy variable for Catholics, for Protestants, and for the other religious denominations, so we can include those 3 dummy variables into our regression model, and then for each of those dummy variables we get a regression coefficient, so B1, B2, and B3. So what is the predicted value in this case, for instance, for the Catholics? Well, it's again B1, the constant, it's the same for everybody, plus the coefficient for our Catholic dummy, so the B1 coefficient multiplied by 1. Why multiplied by 1? Because we gave everybody that indicated that belonged to a Catholic denomination the value 1 in our data set. Yeah, plus B2, the regression coefficient for being Protestant, multiplied by 0. Well, why? Well, we are looking at the predicted value for Catholics. They are Catholics and therefore not Protestant, so they got the value 0 on the Protestant dummy that we created in our data set. So B2 is multiplied by 0, and the same goes for B3, the regression coefficient for the dummy variable for other religious domination, because the Catholics do not belong to other religious denominations, they belong to the Catholic religious denomination. So again, the regression coefficient B3 is multiplied by 0. Well, as always, if you multiply it by 0, something by 0, you get 0, so you can drop it from the equation. So in other words, what is the predicted value for Catholics? Well, it's the constant B0 plus B1 times 1, because they are Catholic. So that B1 coefficient is multiplied by 1, and that is added to the constant. Predicted value for Protestants, well, it's B0, again, the constant, that's the same for everybody, plus the regression coefficient for the Catholic dummy, so the B1 coefficient, multiplied by 0, because these people are not Catholics, they are Protestants, so they got a 0 on the dummy variable for being Catholic, plus B2 multiplied by 1. B2 is regression coefficient for the Protestant dummy. Well, these people are in fact Protestants, so they got the value 1 on that dummy variable. So for them, the regression coefficient B2 is multiplied by 1, and plus B3 times 0, because these people do not belong to other religious denominations. So the dummy variable other for these people took the value 0. So the coefficient for B3 for the other religious denomination dummy is multiplied by 0. So in other words, the predicted value for the Protestant works out to, again, the constant plus B2 plus the regression coefficient for being a Protestant, because all the other regression coefficients are multiplied by 0 and therefore drop out of our regression equation. And again, we can do the same thing for other religious people, so the people that fall in the other religious denominations. What is the predicted value? B0, the constant, plus B1, the coefficient for being Catholic, multiplied by 0 because they are not Catholic, plus B2, the coefficient for being Protestant, multiplied by 0 because they are not Protestant, plus B3, the regression coefficient for belonging to other religious denomination, multiplied by 1 because, yes, in fact, they do belong to those other religious denominations. So that regression coefficient is multiplied by 1. So in other words, for the predicted value for other religious people is B0, the constant, plus B3 times 1. So just plus B3. And then what is the predicted value for the non-religious people? So in other words, the reference category, the people that are not captured by our three dummy variables. Well, it's B0, the predicted value that, the constant value that everybody gets, plus B1, the coefficient for being a Catholic, multiplied by 0 because these people are not Catholic, plus B2, the coefficient for being Protestant, multiplied by 0 because these people are not Protestant, plus B3, the regression coefficient for belonging to other religious denominations, multiplied by 0 because these people also do not belong to other religious denominations. They don't belong to any religious denominations. They are non-religious. So also that B3 coefficient is multiplied by 0. So in other words, what is the predicted value for people that are non-religious? It's B0. It's just a constant value. Yeah, so you can really see how because we already have those 3 dummy variables for Catholic, Protestants, and others, and we just have 4 categories and they are mutually exclusive and exhaustive. That means information on the predicted value for the remaining category, for the reference category, is the B0 coefficient, is contained in the B0 coefficient, in the constant of our regression equation. So let's look into this example even more in concrete terms. Let's say I've estimated my effect of gender on trust in parliament, and as a matter of fact I did that with some old European social survey data. So here you see I've estimated the regression model. I took trust in countries' parliament as dependent variable, and I made a dummy variable for female, and I indicated, well, this is a dummy variable for female and male is used as the reference category. And I got these estimates. So I got a B0 coefficient of 5.354 and a B1 coefficient for the female dummy of minus 0.0301. Okay, so how do we interpret this? Well, what is the predicted value? The predicted value is, for each case, is equal to the constant, so 5.354 minus 0.301 times the value on the female dummy variable that we created on our data set. So again, we can calculate predicted values like we would always do in regression models, just work out the formula for each case. Well, what is the predicted value based on the regression coefficients multiplied by the observations on the X variables that we included, plus the constant value that we add to that. So the predicted value for men in this case, well, works out to, well, the constant value, B0, plus B1, the coefficient for female, multiplied by 0 because these people do not belong to the female category. So for them, because we created this dummy variable indicating for these persons the value 0. So for them, it's 5.354 minus 0.301, the regression coefficient for the female dummy, multiplied by 0. Yeah, multiply something by 0, you get 0, so you can just forget about it. You can drop it out of the equation. So in other words, the predicted value for men is simply the constant. Why? Well, because we picked men as the reference category in this example. And what is then the predicted value for women? Well, again, fill in the formula, 5.354, the constant value, minus 0.301 multiplied by 1, because we assigned to those cases the value 1 on the dummy variable for female. So in other words, that works out to a predicted value of 5.053. So now we know, based on our regression coefficient, that what does that regression coefficient capture? What does it mean, this regression coefficient for the female dummy? It tells us what the difference is in predicted value for men for women compared to men. The predicted value for men is the constant. The predicted value for women is the constant, in this case minus 0.301. In other words, our regression model now tells us that the predicted value on trust in parliament is 0.301 points lower for women than for men. Yeah, again, you need to always interpret these effects relative to the reference category. Yeah, so in this case, the 0.301, this tells us about the difference between people that belong to the female category in the data set relative to the reference category, the male category. Yeah, and in this case, all the other things stay the same. So in this case, we see again, we get a p-value based on the coefficient divided by the standard errors. So that's the t-value compared to the distribution. That gives us the p-value. And we can still reject or not reject a null hypothesis that b1, the coefficient, the regression coefficient for the female dummy in the population, equals the value 0. So in this case, we see that it's a quite small p-value. So in this case, we would probably want to reject that null hypothesis, which, if you think about that, what would that null hypothesis mean? That B1 is 0 in the population, that this regression coefficient for female is exactly the value 0 if we would have had all the observations in the population. It basically means that there are no differences in the population between men and women in trust in parliament. So in this case, we can reject that null hypothesis in favor of the alternative hypothesis that women are in fact less trusting in parliament than men, that the predicted value is in fact lower in the population. Yeah, and in our sample, it's lower by 0.301 points. Another way to think about this is that these dummy variables kind of capture or represent shifts in the intercept of our regression equation. Because, well, let's consider a fictional example. Let's say we are estimating the effects of income and also social class at the same time. So we have a regression model. Let's say our dependent variable is trust in parliament, and we have included income as a continuous variable. But we also included socioeconomic class of people. And let's say we assumed that class could be measured in 3 categories, so lower, middle, and higher class. And we picked the lowest class, the lower class, as the reference category. So we chopped up socioeconomic class into 3 categories, lower, middle, and higher. And we picked the lowest one as the reference category, meaning that we created 2 dummy variables, one for the people in the middle class and one for the people in the higher class. And again, we also included a linear effect for our income variable, which we assume is going to be a continuous variable. Then let's assume these were the regression coefficients that we found. I made these up, so these are not based on actual data. This is just to have an example that we can work with. So let's consider how could we think visually about that effect. Well, all these individual stars would represent the individual observations, and both based on those observations, we have estimated this regression model, which will give us the effect of income. So that's the regression line that we plotted. The regression coefficient is 0.05, so that means for every 1 unit increase of income on whatever scale that is measured at leads to an increase in the predicted value on trust in parliament by 0.5 points. Yeah, so it's a positive effect in this case. More income leads to a higher predicted value on trust in parliament. And we know where that regression line intersects with the y-axis, because that's given by the constant value of 5.6. Yeah, so we know for people with 0 on income and all the other variables, the predicted value is 5.6. And then for every 1 unit increase on income on its scale, we can add 0.5 points to the predicted value on trust in parliament. So let's assume this regression line that I plotted now, that this would show the income effect for the lower class people, because that's the reference category. So for that category, we can even forget about middle class and higher class. We can only look at the effect of income, because for the reference category, the middle class dummy takes the value 0. So the regression coefficient for middle class would be multiplied by 0 and just becomes 0, and the higher class dummy would take the value 0 and thus is multiplied by 0 and gets the value 0 and can be dropped from the equation. So for for people in lower class, we can think of this regression model as saying, well, we have a constant value of 5.6, and that's for people with 0 income, and for every one additional unit of income, the predicted value for these people increases by 0.5 points, because that's the reference category. Now, for the middle class, we get the same income effect. There is no difference in that. Yeah, we are not somehow allowing that income effect to be different for middle class or for higher people. So they still have the same increase in predicted value for every 1 unit increase in income. So they still have the same income effect that's relevant for them. But for the middle class people, we also find that we now need to take into account the regression coefficient that we found for the middle class dummy, which was in this example 1.2. And we know that for those people in the middle class, they score a 1 on the middle class dummy. So for them, we can add 1.2 times 1 to the predicted value. In other words, we are shifting up the intercept of our regression equation from 5.6, which was the intercept for the lower class people. We are shifting that up by 1.2 points. Well, 5.6 plus 1.2 works out to 6.8. So in this case, we see that by including this dummy variable, we are basically pushing up the intercept by a second constant value, in this case by a constant value of 1.2. And conversely, for the higher class people, again, the income effect stays exactly the same, but we see that we find a regression coefficient for the higher class dummy of minus 0.5, meaning that for all those people that are in the higher class, we are basically shifting the intercept of our regression equation downwards by 0.5 points. Yeah, so 5.6 minus 0.5 works out to 5.1. So in other words, we see that the intercept for this income effect is lowest for the higher class people, so they have an intercept of 5.1. It's a bit higher for the lower class people, they have an intercept of 5.6, and it is quite a bit higher for the middle class people, they have an intercept of 6.8. Yeah, so that's another way of thinking about how can we interpret these dummy coefficients. Well, they just add a constant value for one specific categories of cases, so we can just think of them as adding an extra constant on top of our already existing constant value of our B0 coefficient for those specific cases that fall within that category. So basically just shifting our intercept up and down by the value of the coefficient of that dummy variable. So let's look at a much more elaborate example. So now I've re-estimated my model for trust in parliament and now included age as a continuous variable. I included the dummy variable for female, and I also included the dummy variables that I created for religious denomination. So now I have a much more elaborate model. Maybe I want to control for differences in age, and I want to test hypotheses about both gender as well as religious denomination. So yeah, great, awesome. We can throw all of these different variables into our regression model. Yeah, so notice now our regression model is actually about 3 independent variables: age, gender, and religious denominations. But it actually includes, in reality, it actually includes 1, 2, 3, 4, 5 different variables and coefficients, because we have one variable for age, so we get one coefficient for age because we treat that as a continuous variable. We have one coefficient for female because, yes, it's a categorical variable, but the ESS reduced that to 2 categories. So we only need one dummy variable to capture that gender effect. But we actually needed 3 different categories to capture the religious denomination effects because we disentangled that into 3 different potential categories: Catholic, Protestant, and other. Yeah, so, okay. This is the effects that I got for estimating this regression model. So how do we interpret these dummy coefficients now? Well, let's start with the dummy coefficients for the religious denomination effect. Yeah, how do we now interpret this? So let's say we are treating age and gender as control variables, and we want to now interpret the effects of religious denomination. Well, as always, if we included other variables in our model, we can interpret the effects as controlling or adjusting for differences on these other variables, adjusting or controlling for the effects of these other variables on our dependent variable, and then that stays exactly the same, and then we can just interpret our regression coefficients in terms of predicted values as we always do. So in this case, controlling for the effects of age and gender, the predicted value on trust in Parliament is, well, it is 0.268 points higher for Catholics than for non-religious people, because the value we got for the regression coefficient for the Catholic dummy is 0.268, and the reference category that we picked for the religious denomination is not religious. So now this regression coefficient of 0.268 tells us by how much the intercept of the regression equation is shifted upwards for the Catholic people. So how much higher the predicted value is for Catholic people than for the non-religious people, because those are the people that's the category that we choose as the reference category. So we always have to interpret these effects as relative to the reference category that we picked. Yeah, so in this case, the predicted value on trust in Parliament is 0.268 points higher for Catholics than for the non-religious people, and it is 0.334 points higher for the Protestants than for the non-religious people. Again, we picked the non-religious people as the reference category, so we have to interpret all of our dummy coefficients as relative to that category. So the coefficient that we found for the Protestant dummy, the B4 coefficient, worked out to be 0.334. That tells us by how much the intercept is shifted for people that are Protestants. So by, in this case, how much higher the predicted value on trust in Parliament is for Protestants compared to non-religious people, controlling for the effects of gender and age on trust in Parliament, because those are also included in our model. And lastly, we also find a coefficient for the other religious denominations. It's a negative coefficient that indicates the predicted value in our sample for non-religious people is lower than for the non-religious people, and happens to be lower by the same amount that it is higher for the Protestant people. So that's just a coincidence. So in this case, we see that the predicted value in our sample for the other religious denominations is actually 0.334 points lower than for the non-religious people, controlling for the effects of age and gender on trust in Parliament. But you also see that for that category, you find a quite high p-value. So in that case, you would probably not want to reject the null hypothesis that the coefficient B5 is 0 in the population. In other words, we find no significant difference between the non-religious people and the people in this case that belong to religions other than Catholicism or Protestantism, so the other religious denominations. Now, a couple of remarks on working with dummy coding. One is interpreting these effects of dummy variables by looking at the unstandardized coefficients is great. Don't try to interpret the standardized coefficients, so what we sometimes refer to as the beta coefficients. Why? Well, remember, what are these standardized coefficients? What do they represent? They represent the effects of our x variables on our y variables if we would have standardized those variables. So if we have calculated z-scores for our y and our x variables and our y variable. And how do you do that standardization? How do you calculate z-scores? Well, you calculate the difference between the mean and the observations and divide that by the standard deviation. But if you're talking about categorical variables, this way of talking about variation, talking about variance and standard deviations really isn't meaningful. That works for continuous variables, the way we normally calculate variances and standard deviations. But it really doesn't work for categorical variables. So if the standard deviations, the way we normally do them, is not meaningful, then standardization is also not meaningful. So these standardized coefficients can't sensibly be interpreted for dummy coefficients. So even though SPSS is giving them to you, don't even try to interpret them, because they have no meaningful interpretations. And the other thing, the other reason why it really makes no sense to look at the standardized coefficients is if you have more than one dummy variable. Yeah, so for instance, in our example, we had religious denomination in 4 different categories. So you get 3 different dummy coefficients. Well, how are you now going to make a conclusion about, well, what is then the overall size of the effect of religious denominations, of being religious? There are solutions to these problems. This is, for instance, the so-called sheaf coefficients. That's beyond what we are going to cover in this course. But if you want to write a paper or a thesis and you really want to say something about how can I compare effect sizes having categorical variables, then that's something you could take a look at. The other remark I want to make about that is watch out with what I would call messy categories. So for instance, if you are combining all kinds of different groups into some other category, because you want, of course you need your categories to be exhaustive, so you somehow have to cover all the cases. But often you will be in a situation where there are some main categories for which you can create dummy variables for which you have lots of observations, and then there will be lots of other smaller categories for which you have so few observations that it doesn't make sense to create a dummy variable because there aren't enough observations to have any kind of meaningful distinction between those cases, at least not statistically. So what you then need to do is you need to somehow group them into this other category, which we did in our example with the other religious denominations. Not because we don't care about these other religious denominations, but because they are so small that if you take a sample from the Dutch population, then the number of cases you have within that sample within each of those smaller religious denominations is so small that you can't really meaningfully statistically analyze these differences, but you still somehow need to have a category that covers those cases, so you create this other category, and that's often something that you will often have to do. But of course that also means that these are very messy categories because they combine all kinds of different cases that we weren't able to categorize under the other categories. So I would be very hesitant to overinterpret effects of such dummy variables because they are inherently very noisy measurements. And also categories that have very few cases. So sometimes there's no getting around that there's just a couple of cases left that you somehow cannot cover within the other categories, and you still want to use them in your analysis. Well, then you might have some very small categories where you have just a few observations. Again, because you have so few observations, the regression coefficients that you get for these categories will be super noisy, super unreliable. So I would be very careful with not overinterpreting the effects of such messy or small categories, these dummy coefficient effects. And I definitely would recommend against ever using such categories, so messy or small number of observations categories, as reference categories, because how do we need to interpret the effects for these dummy variables? Well, that's always relative to the reference category. So if our reference category is a super noisy or messy category, or a category where we have very small few observations, meaning that the estimates for that for distinguishing that category are super unreliable, then if we take that as a reference category, then all the other effects that we find are also going to be super unreliable because we are now comparing to that messy or small category. So try to avoid using messy or small number of case or categories where you have small number of cases as reference categories. One thing that's super useful about dummy coding, that even if you have continuous variables, sometimes it makes sense to dummy code those continuous variables, even if you wind up not using those dummy coded x variables, but just as a check. So one thing that you can do is you can actually use dummy coding to check whether it's okay to assume a linear continuous effect for your x variable. How to do that, I'll show you in the B lecture of this week. So I'll show you one or two examples of when that works, but I just wanted to already tell you that this is coming up, that you can actually use dummy coding to check whether it makes sense to treat them as continuous, or also to treat them as continuous variables with linear effects, because you can also use this trick to check whether it might make sense to more sense to consider the effects as being non-linear in some way. Okay, so that's for categorical x variables. Now let's take a couple of careful steps into, well, what if our dependent variable is categorical? Would that ever happen? Would that ever be interesting? Well, what is the stuff that political scientists care about? They want to analyze whether or not countries are at war, which is a categorical variable. They want to analyze whether or not people vote in an election, which is a categorical variable. They want to analyze whether or not people voted for some political party, which is a categorical variable. They want to analyze whether or not trade unions call strikes, which is a categorical dependent variable. They might want to analyze whether or not people are members of a trade union, which is a categorical dependent variable. They might want to analyze whether or not a country adopts a certain policy, which is a categorical dependent variable. They might want to analyze whether or not a dyad of two countries, so a combination of two countries, is at war or not, which again is a categorical dependent variable. In other words, I mean, these are just a couple of typical examples you will see in political science, both in comparative politics as well as in international relations research, where the thing that people want to explain, that political scientists want to explain, are things that are really categorical outcomes. Something happened or something did not happen. There are different categories on our dependent variable. So, okay, great. So far we have assumed that our dependent variables are continuous. But now we see that, well, most of the stuff that political scientists tend to care about is stuff that's measured categorically. So, yeah. What about that? Well, the good news is that we actually can analyze categorical Y variables. And one way of doing that is using so-called logistic regression models. Yeah, so that's what we're going to discuss a lot in the remainder of the course. And we are only going to consider one specific situation. We are only going to consider the simple situation where something either happens or it doesn't happen, and you want to explain that. So we are then talking about what is sometimes referred to as dichotomous Y variables. Dichotomous variables meaning that there are only two situations possible. Something happened, some event happened, or the event did not happen. And for that we are going to use a specific version of logistic regression, which is referred to as binomial logistic regression. Why am I saying that? Well, because there are also categorical variables that you might be interested in that have more than two categories, where it's not just that something happened or something did not happen, but there might be more than two categories that are possible for the cases. Yeah, maybe you want to analyze what party people voted for, and there are lots of different parties they could have voted for, including maybe not voting for any party at all. So then you would have more than just two categories. And the great thing is logistic regression can even be extended further in different ways to actually deal with those situations as well. So if we're talking about categorical dependent variables with more than two categories, then we can use something called the multinomial logistic regression model. And if we have categorical variables where there is actually a logical order between the different categories, so we can treat the different categories as indicating being smaller or larger on some scale. It's just that the steps are not strictly equal and it's not really a continuous variable. Then there is also another way of extending logistic regression model, which is the so-called ordered logistic regression model. Yeah, so we are not going to go into that in this course already, because that means that we first have to really understand quite well how binomial logistic regression works. So that's what we're going to go over in this course. But the good thing is, once you know that really, really well, it's quite easy to pick up these more extended versions for categorical and ordinal dependent variables, which might be interesting for you if, maybe for your thesis or for your research paper, you want to be a bit more sophisticated and not just reduce everything to just something either happens or it doesn't happen, but take into account that there might be more interesting categories in your dependent variable. So before we even get into talking about logistic regression analysis any further, we need to really get down the basics. We really need to make sure that we understand some very basic things. Specifically, there are a couple of different concepts that you really need to have internalized before we can really meaningfully discuss logistic regression. And that is probabilities, odds ratios, and something that's really mathematical, logarithmic transformations. I'm going to make a start with that today by talking about the first three things on this list: probabilities, odds, and odds ratios. So let's start very basically. What do we mean when we talk about probability? Well, if we talk about probability from a statistical perspective, there is a very specific meaning to the word probability. And that meaning basically is that the probability is supposed to capture how likely it is that some event occurs. Yeah, so we want to analyze some event, and the probability signifies, well, how likely is it that this event happens? Which means that we can actually translate the probability into a precise formula. And that formula is that if we want to describe the probability, then that equals the number of events divided by the number of observations. Yeah, so we have a categorical variable where something either happened or it didn't happen. So the event either occurred or it didn't occur. Yeah, so the event could be anything. It could be people voted, or people are a member of a party, or it could be countries are at war. Okay, then what is the probability? Well, it is the number of events that we observe divided by the total number of observations that we have. So in other words, how likely is it that some event occurs means that, well, how often did it happen? So that's number of events divided by, well, how often could it have happened? The number of observations. In other words, the probability is also a proportion. It is a proportion of observations where the event that we're interested in actually occurred. Very important to already note at the start, probabilities are bounded at 0 at 1. So a probability can never take a value that's smaller than 0, and it can never take a value that's larger than 1. That's going to be important later on to know, but for now it's maybe good to understand, well, why is that the case? Why can't the probability ever be smaller than 0? So why can't the probability ever be a negative number? And why can't the probability ever be a positive number larger than 1? Why is that impossible? Well, look at the formula. How do we calculate the probability? Number of events divided by number of observations. Now, hopefully you will agree with me that it could never be the case that something happens more often than always. So it should never be possible that the number of events is actually larger than the number of observations. So at the most, all the observations that we observe experience the event that we are interested in. So in that case, the probability would be 1. And conversely, things cannot happen less often than never. So the number of events can never be such that that we get a negative result, right? So in other words, our probabilities can't be less than 0, because 0 already implies that of the total number of observations that we have observed, 0 of those actually experience the event. So number of events would then be 0. So then the probability is 0. Later on, it's going to be important to remember this point, but for now, it's important to just realize it. Now, if you would code your variable in such a way that you give the value 0 to the cases where the event did not occur, and the value 1 to the cases where the event did occur, so in other words, use dummy coding for such a variable, then there is a nice trick that, again, for now you should just be aware of. Later on this will come in useful. And that is, well, if you would then calculate the mean value of that variable, then the mean value of that variable would be the same as the proportion of observations where the event occurred. Because, well, how do we calculate the mean value? Well, you add up all the individual observations and divide by the size of the sample. And if we dummy code, so 0, 1 code our variable y, then adding up all the observations means for each case, we are going to add up the value of that case for our variable y. So for all the cases that did not experience the event, they get the value 0. So for all of those cases, we just add 0, 0, 0 plus 0 plus 0 plus 0 plus 0 plus 0. And for all of the cases that did experience the event, because we gave them a 1 in our coding scheme, in our dummy coding, for them, we add up the observation, which is 1, because that's the value we gave them. So for all the cases that did observe the event, it's 1 plus 1 plus 1 plus 1 plus 1 plus 1. Yeah, so in other words, then the top part of the fraction is just the number of events that we have. And then in all of these formulas, so whether we are talking about the mean or the probability or proportion, we are dividing by the number of observations. So that means that if we dummy code our y variable, then if we would calculate the mean of that variable, that would be identical to the proportion of observations where the event occurred, which is the definition of the probability that the event occurred. So let's look at some concrete examples. So we know what the abstract formula is, the number of events divided by the number of observations. Now let's consider the example where we say, well, we have a sample of 300 people, and the event that we're interested in is voting. So we observed 150 of those people did vote, and 150 of them did not vote. Okay, so what is now the probability of voting based on this sample of 300 people. As always, first think for yourself. How would I solve the formula? What would the result be? Well, again, what is the formula for probability? Number of events divided by the number of observations. So we have 150 people that experienced the event. So they did vote. They experienced the event of voting. So we have 150 events divided by how many observations? 300 observations. So in other words, the probability works out to 0.5. Okay, what is the probability of not voting? Again, stop, think for yourself. What would be the probability of not voting? How would I need to calculate that? Great, you probably figured out that it works out to exactly the same thing. Again, probability of not voting, well, how many people experience the event of not voting? Well, 150 people experience the event of not voting. So the number of events is 150 divided by the number of observations, which is 300, because we have a sample of 300 people, works out to a probability of not voting. That is also 0.5. Let's say it's a little bit more complicated. Let's say we have a sample of 120 countries that we observed, and we see that 12 of those countries are at war, and 108 of those countries are not at war. What is the probability of a country being at war? Again, stop and think. What would be the probability of a country being at war? How would you need to calculate that if you fill in the formula for calculating a probability? Yes, great. We have 12 countries that are at war, so 12 countries experience the event of being at war. In total, we have a sample of 120 countries, so it is 12 events and 120 observations, so it's 12 divided by 120 works out to a probability of being at war of 0.1. Again, well, what is the probability of not being at war, of countries not being at war? What would be that probability? Well, again, fill in the formula, right? We have 108 countries that experience the event of not being at war. So what is the probability of not being at war? It's 108 divided by our sample size, by the total number of observations, 120, which works out to 0.9. This one maybe you have to think about a little bit more. I don't know how many trade unions I did observe, in fact, but I know that of all the trade unions that I did observe, 1 in 4 of those trade unions called for a strike. Yeah, so what is now the probability that a trade union calls a strike? Great, it's 1 divided by 4. Yeah, because for every 4 observations of trade unions, 1 of those trade unions called for a strike. So the probability of striking is 1 divided by 4, which works out to a probability of 0.25. What is the probability for trade unions to not call a strike? Well, again, how many events do we have? Well, 3 in 4 trade unions did not call for a strike. So it's 3 divided by 4 is 0.75. Yeah, so that's how to calculate probabilities. And you will notice that if you look at those different probabilities that we can calculate, that the sum of all probabilities for a specific event is always 1. Yeah, so if you look at the voting example, the probability of voting is 0.5. The probability of not voting is also 0.5. And in this case, those are the same probabilities because it's exactly split down the middle. But if we add up those two probabilities, so the probability of not voting plus the probability of voting, then we get the value 1. Yeah, so the probability of being at war for the countries in the example, well, we have a probability of being at war of 0.1. We have a probability of not being at war of 0.9. And add those together, you get a 1, because then again we're covering all the countries. Which also means that if you know one probability, you can always just calculate the other probability by saying, well, 1 minus this probability is the probability of the other outcome. Yeah, so considering the at war example, so we know that the probability of a country being at war is 0.1, then we know by definition the probability of not being at war is 1 minus 0.1, because that has to be the remaining probability, which works out indeed to 0.9. So that's about probabilities. Now let's go a step further. Now let's talk about something that those of you that are really into betting know a lot about already. Odds, because betting often talks about not probabilities, but it talks about odds. So what are odds? Odds are also a measure of likeliness, but they are a relative measure of likeliness. So it is a measure of how likely is it that some event that we're interested in occurs relative to how likely is it that that event does not occur. Or in other words, how likely is it that something happens relative to how unlikely is it that something happens. Well, we already saw the probability measures, well, how likely is it that something happens? So if we want to calculate how likely it is that something happens relative to how likely it is that something does not happen, how would we calculate that? Well, take the probability that some event occurs and divide that by the probability that that same event does not occur. So that's what the odds are. They tell you about how relatively likely it is that something happens compared to how unlikely it is that something happens. So what is the probability that some event that we're interested in occurs relative to the probability that that same event does in fact not occur? In other words, we can always calculate that by saying, well, the probability that the event happens, so P, divided by 1 minus P, the probability that that same event does in fact not happen. Again, the total probabilities have to sum to 1. So once we know the probability that some event does happen, we know we can just calculate the probability of that same event not happening as being 1 minus that probability of the event happening. So P divided by 1 minus P, that is what the odds are. How likely is it that something happens relative to how unlikely is it that something happens. And odds again have a natural limit. They cannot ever be smaller than 0. Because probabilities can never be smaller than 0, so there's no way that the odds can ever be smaller than 0. But they can go in the positive direction all the way up to infinity, basically. So it could be always ever more relatively likely that something happens compared to how relatively unlikely it is that something happens. So you can push up the p-value ever further and ever further and ever further, which means that you will ever further decrease 1 minus p. And then basically you can get an ever larger ratio of p divided by 1 minus p. Yeah, so probabilities are bounded between 0 and 1. Odds are only bounded at 0, but can in theory go up to infinity. Yeah, so the closer you move your probability to being the perfect one, the more your odds will increase towards infinity, basically. Yeah. So again, this is going to be useful later on to know this property already. So again, let's look at a concrete example. So let's look at how do we calculate odds. So let's say that we already know that the probability of a country being a democracy is 0.5. Well, okay, great. That's probability. That's how likely it is that countries are democracies. How likely is it that countries are democracies relative to that they are not democracies? So what are now the odds of democracy? Well, again, stop and think for yourself. Filling in the formula, how would you do that? How would you calculate the odds of being a democracy? Well, we know that the probability of being a democracy is 0.5. So we know that that probability is 0.5. So the odds has to be 0.5 divided by the probability of not being a democracy. So 1 minus 0.5. In other words, that's 0.5 divided by 0.5, which works out to an odds of 1. So in other words, we can now interpret this 1 as indicating that the probability of a country being a democracy is exactly identical to the probability of countries not being democracies. In other words, it's relatively as likely that countries are democracies than that they are not democracies. In this case, we would say the odds are even in the sense that both of these outcomes are relatively equally likely. So what are the odds in this case of countries not being a democracy? Yeah, again, it's exactly the same result, right? Because the probability is exactly 0.5. So if you want to calculate the odds of countries not being a democracy, and I forgot the D apparently in democracy, then how do we calculate that? Well, again, take a look at the probability, divide that by 1 minus the probability. So in this case, probability was 0.5. So 0.5 divided by 1 minus 0.5 works out to 0.5 divided by 0.5, which is 1. In other words, in this case, we would say the odds are exactly even. So it's the odds of being a democracy is identical to the odds of not being a democracy because the probability is exactly 0.5. So let's make it a little bit more interesting. Let's say we know that the probability of not voting, yeah, very careful, the probability of not voting is 0.2. given that we know this, what do we know about the odds of not voting? How do we calculate the odds of not voting? Again, stop and think for yourself first, before you hit pause again, before you hit play again. Yes, well, fill in the formula. We know that the probability of not voting is 0.2. So how do we calculate the odds of not voting? Well, 0.2 divided by 1 minus 0.2. So that's 0.2, the odds, the probability of not voting divided by 1 minus the probability of not voting. In other words, the probability of yes voting. So that's 0.8, because 1 minus 0.2 works out to 0.8. So 0.2 divided by 0.8 works out to 0.25. So the odds of not voting are 0.25, indicating that it is relatively less likely to not be voting than it is likely to be, in fact, voting, because we see that the probability of not voting is smaller than the probability of voting, meaning that the odds are smaller than 1. What then, based on this information, that the probability of not voting is 0.2, would be the odds of yes voting, that people do vote? Again, pause, think for yourself first. Yeah, it's the other way around. If the probability of not voting is 0.2, then the probability of voting has to be 1 minus 0.2, which works out to 0.8. And then dividing 0.8, the probability of voting, by the probability of not voting, 0.2, works out to 4. Yeah, so basically it is 4 times as likely that people do in fact vote than it is that they do not vote. So that's how you can interpret these odds. How relatively likely is it that whatever the event is that we're analyzing happens, compared to how unlikely it is that that event happens. One more, just for practice. Let's say we have a sample of 100 diets of countries. Yeah, diets just meaning combinations of 2 countries. And we have observed that 10 of those diets, so combinations of 2 countries, are at war. Yeah, so that we have basically 10 countries that are 10 combinations of countries where the countries are at war with each other. So that's an often used dependent variable in international relations research. Well, given that we know this, what is the odds that diets of countries are not at war? So what are the odds of not being at war? Again, stop, pause, think for yourself first. How would you calculate that? What would be the result? Well, that was probably quite difficult for you, but yes, it is 0.9 divided by 0.1. Why 0.9? Well, we know what the probability of being at war is, because 10 diets are at war. So that means 10 out of 100 diets are in fact at war, so the probability of being at war is 10 divided by 100, which works out to 0.1. Which means that the probability of diets not being at war is 1 minus 0.1, which works out to 0.9. So if we want to calculate the odds of not being at war, we start with, okay, 0.9, that's the probability of not being at war, divided by 1 minus that probability, so divided by 0.1, which works out to 9. So in this case, we see that the odds of not being at war is 9, meaning that it's 9 times as likely to not be at war than it is to be at war for countries. Yeah, so that's how to interpret these odds. And then again, what would be the odds of yes being at war? Stop, pause and think. Yeah, it's 0.1 divided by 0.9, so the probability of being at war is 0.1, the probability of not being at war is 0.9, 0.1 divided by 0.19 works out to round about 0.11. So those are odds. Well, why do we care about odds? Well, they are interesting in the sense that they convey a sense of relative likeliness, which itself can already be interesting. But for you, the most important thing is you need to understand odds, because you need to understand odds ratios, because odds ratios are going to be fundamental in understanding how to analyze effects of categorical variables. So an odds ratio is a measure of association, like the correlation coefficient is also a measure of association, meaning it measures the association between variables. And it is expressed as the change in the odds that the event occurs with a change of 1 unit in x. So that is basically what the odds ratio is measuring. And we'll start with a very simple example today, where our x variable will also be a categorical variable with just two possible categories. So there's only one change that we can see in our x variable of 1 unit. So either something did happen or something did not happen. So that's what we'll start out with today. So that's the odds ratio. It's a measure of association that's basically expressed as changes in odds, meaning that you have to understand what odds are in order to understand the odds ratio. Which also means that the odds ratios follow the same mathematical rules as those of the odds. Odds ratios can't ever be smaller than 0, but they can go to infinity. So they are bounded at 0 because the odds are also bounded at 0, because odds can't be negative. Odds ratios also can't be negative, but they can in theory go up to any number. In theory, they can go up to infinity. So how do we interpret them? Well, very basically, an odds ratio of 1 indicates that there is no association. An odds ratio smaller than 1 indicates that there is a negative association. And an odds ratio of larger than 1 indicates that there is a positive association. That might be a bit surprising if you have never heard about odds ratios before, because you have probably learned a lot about correlation coefficients and regression coefficients, and you are used to thinking about no association being identical to the value 0, and positive associations being identical to a positive value, and negative value associations being identical to a negative value. Now for the odds ratio, it's really different. For the odds ratio, no association is captured by the value 1. Negative associations are some value between 0 and 1, so some value that's smaller than 0, but it needs to be, it can't ever be smaller than 0. So some positive number that's smaller than 1, and positive associations are positive numbers that are larger than 1. Yeah, so that's the basic interpretation of odds ratios on abstract level. So now let's look into a concrete example to get a handle on why is that? Why do the odds ratios, how do they work the way they work? So I created here a fictional example. Let's again, I totally made these data up, but let's say I was interested in, well, what is the association between unemployment and trade union membership? Maybe I have some theory that tells me, well, it's maybe less likely for unemployed persons than for employed persons to be a member of a trade union, because trade unions are really all about taking care of the interest of employed persons, so that might not be super relevant for unemployed persons. So maybe I want to see, well, what is the association between unemployment and trade union membership? And let's say I collected a data set, there's some questionnaire survey, for instance, where I ask people whether or not they are members and whether or not they are employed. So I have two variables, employment and trade union membership, and I want to figure out, well, what is the association between those two variables? So again, it's a fictional example, but let's say I have 750 observations in my sample. So that's the total number of observations that I have, and I see of those 750, 500 are members of trade unions and are also employed. And 120 are members of trade unions but are unemployed. So in total we have 620 people that are members of trade unions. And I see that 50 of the employed persons are not members of a trade union, and 80 of the unemployed persons are not members of the trade union. In total we have 130 people that are not member of a trade union. And we see that in total there are 550 people in our sample that are employed and 200 people that are not employed. Okay, so now how can I analyze the association between employment and trade union membership, or unemployment and trade union membership? And well, why do we need an odds ratio to say something about this relationship? Why can't we just look at how the probabilities of membership differ between the employed and the unemployed? Well, that's because the probability of membership also depends on the overall distribution of employed and unemployed persons and members, non-members in our sample. So that's really not directly comparable. So the odds ratio is really a trick to make it somehow comparable by translating probabilities into odds and then looking at ratios of odds to express the association that we are interested in. So let's do this really step by step. So let's first consider the employed persons in our data set. So we have 550 employed persons, 500 of those are members of a trade union, 50 are not members of trade unions. What would be the probability of membership for employed persons? So what is the probability that people that are employed in my sample are also members of a trade union? Again, stop, pause and think for yourself first. Yes, we have 500 people that are members among the employed persons. So among the employed persons, 500 experience the event of yes trade union membership, and the total number of observations that we have is 550. So the probability of membership for employed persons is 500 divided by 550, which works out to round about 0.91. Okay, so now we know the probability of membership for employed persons. What are the odds of membership for employed persons? Again, stop, pause, and think. What were the odds again? How do we calculate them? Well, maybe some of you are still awake and alive. Yes, the odds of membership are round about 10.11 because we know that the probability of membership is round about 0.91. So we know that if we want to calculate the odds of membership for these people, then we need to take a look at that probability divided by 1 minus that probability. So the probability of membership relative to the probability of not being a trade union member. So 0.91 divided by 1 minus 0.91, which works out to round about 10.11. So the odds of membership among the employed persons are 10.11, meaning that employed persons are about 10 times more likely to be a trade union member than to not be a trade union member. And we can do the same thing for the unemployed persons. Well, what is the probability of trade union membership for people that are not employed? Again, stop, pause, and think. What is that probability? Yes, 120 divided by 200, because 120 of the people that we observed that are unemployed are in fact members of trade unions. And the total number of people that we observe that are unemployed are 200. So what is the probability of trade union membership for the unemployed? Well, we have 120 events, membership in this case, and we have 200 observations. So 120 divided by 200 works out to a probability of trade union membership of 0.6. Well, again, what does that then mean for the odds of membership? What are the odds of membership for the unemployed persons in our data set? Stop, pause, and think. And yeah, if the probability of membership is 0.6, then the odds of membership is 0.6 divided by 1 minus 0.6, which works out to 0.6 divided by 0.4, which works out to exactly 1.5. So in other words, unemployed persons are 1.5 times as likely to be a trade union member than they are to not be a trade union member. Yeah, so now we see that we have two different odds. We have the odds of membership for the employed persons and the odds of membership for the unemployed persons. And in both cases, we see that the odds is larger than 1. So people either employed or unemployed people both are relatively more likely to yes be a trade union member than no be not a trade union member. But we see by what the size of that odds is differs quite a bit. So we see for the employed persons, they're actually 10 times more likely to be a member than to not be a member, whereas for the unemployed persons, they are only 1.5 times as likely to be a member than to not be a member. So if we now want to calculate, well, okay, now what is the association between unemployment or employment and trade union membership? Well, we can just look, well, what is the ratio of these two numbers? Because that is literally what the odds ratio is. It is a ratio of odds. It is a ratio of two odds. So how many times do the odds for one group fit into the odds of another group? And because that tells us something about the association. So in this case, we have these two odds that we know. We know that the odds for the members to be trade unions are 10.11. We know that the odds for the employed persons to be a member is 10.11. We know that the odds for the unemployed persons to be trade union members are 1.5. So we can actually calculate two different odds ratios. We can calculate the odds ratio where we divide 10.11 by 1.5, or we can divide the odds ratio where we divide 1.5 by 10.11. So let's do both of them and look into, well, what does it mean? If we say 10.11 divided by 1.5, that's one odds ratio that we can calculate. Yeah, literally it's the ratio of two odds. The odds of membership for the employed persons divided, so taking the ratio, divided by the odds of membership for the people that are unemployed. So that's 10.11 divided by 1.5, which works out to round about 6.67. So that's what we can calculate. So that would be one odds ratio that we can calculate. What does it mean? Well, it means that the odds of membership for the employed are 6.6 times the odds of membership for the unemployed. Yeah. So great. So now we actually have something that tells us something about the association between employment and trade union membership. We see that the odds of membership for the employed are actually 6.6 times the odds of membership for the unemployed. So relatively speaking, people that are employed are relatively much more likely to be trade union members than people that are unemployed. So there's a positive association between employment and trade union membership, and conversely a negative association between unemployment and trade union membership, because the unemployed persons are relatively less likely to be a trade union member. As a matter of fact, we could also calculate that ratio, so 1.5 the odds of membership for the unemployed persons divided by the odds of membership for the employed persons. That gives us the number 0.15. Well, what does that number now mean? Well, those are the odds of membership for the unemployed compared to the employed. So in other words, the odds of membership for the unemployed are 0.1 times 5, so 0.15 times the odds of membership for the employed. In other words, unemployed persons are relatively less likely to be members of trade unions than employed persons, right? Because the odds ratio that we find is 0.15. Now, both of these odds ratios tell you exactly the same thing. They are based exactly on the same relationship. The only thing that is different between them is one is comparing employed persons to unemployed persons, whereas the other one is comparing unemployed persons to employed persons. So which one of those you would pick depends well on what makes intuitively more sense based on the hypothesis that you formulated, because mathematically they are completely equivalent. It's the same underlying relationship. So that's really just a matter of, well, what is intuitively more sensical in regard to the theory that and the hypothesis that you are trying to test. Yeah, so those are what odds ratios basically represent. So how relatively likely is it that something happens for one group compared to how relatively likely is it that something happens for another group or category. Super useful because it allows you to really compare these to compare different categories across different categories, which can be super useful if you have categorical independent and dependent variables. Yeah, so that's how you would manually calculate those odds ratios. Now, this was the super long way of doing that, where we first calculate probabilities for each group, and then based on those probabilities we calculated the odds for each group, and then we would take a ratio of those two odds to get the odds ratio. It's great to go through that in that way because it really lays bare, let's say, the intuitive steps that we are taking. There is a mathematical trick to do this much quicker. So once you understand intuitively, substantively what the odds and odds ratios are, you can use also this trick, which is much quicker, and the trick is divide the cross products. So what do I mean when I say divide the cross products? Well, if you think back to this table, we could think about this table as having 4 cells within them that contain really the unique information. So those are the cells that indicate 500, 120, 50, and 80, and the rest of the table is of course just the marginal distribution of these categories. Yeah, so basically all the relevant information is already contained in just those 4 cells where we are looking at the intersection of being employed and a member, and employed and not a member, and unemployed and a member, and unemployed and not a member. So these 500, 120, 50, and 80, these cells within our cross table. So for convenience, we are just going to call the first cell here A. We're going to call the second cell here B. We're going to call the third cell here C, and the fourth cell D. So that's just a convention if you have these 2x2 tables. And if you want to talk about the content of these tables, we just start from left to right on each row and give every one of those a letter. So we have A, that's employed persons that are trade union members. B, unemployed persons that are trade union members. C, employed persons that are not trade union members. And D, unemployed persons that are not trade union members. So what is now a cross product? Well, cross meaning we are going to cross over on our table from diagonally, so from the top left to the bottom right, or from the top right to the bottom left, so cross over on diagonal. And product just meaning, well, a product term, so multiply something. So in other words, there are 2 cross products that we can calculate based on this table. The cross product of A times D, Yeah, so crossing over and taking the product, so multiplying. So the value for A multiplied by the value for D. And we can also have the cross product of B times C. So the value for the B cell multiplied by the value for the C cell. So in a 2x2 table, there are two potential cross products that we can calculate, A times D and B times C. And once we have calculated them, we can just divide those two cross products by each other to directly calculate the odds ratio for us. So for instance, if we want to directly calculate the odds ratio of trade union membership, where we compare the odds of membership for the employed relative to those of the unemployed, well, we just start out with the top cell where the employed persons are, so the A cell, multiply that by the D cell, so 500 times 80, so A times D. So that's multiplied and divided by the other cross product, so 120, the B cell, multiplied by 50, the C cell. So we have two cross products here, 500 times 80, so A times D, and 120 times 50, so B times C. So if you want to calculate the odds ratio of trade union membership, where we're comparing employed to the unemployed, we'll start with the category that comes first in that comparison. So in this case, these are the employed persons, and then just do that cross product and divide that by the other cross product, and then you will get, well, exactly around about 6.67, which is the same result we had before, but now we're just quicker in calculating that result, and we don't have to take any kind of intermediate steps where we first calculating probabilities and odds, but we can just directly calculate it. It also means that you don't get any kind of rounding errors that can add up to across different formulas that you're solving. Yeah, so this is just a mathematical trick. There's no real substantive need to do that. It just makes it easier to calculate odds ratios quickly and a bit more precisely than going through all the steps and rounding in between all the different steps. So again, we can also do this for the other odds ratio from the unemployed relative to the employed. We'll then just start in the cell where the unemployed are, so that's the B cell. Take a look at that cross product, so that's B times C, and divide that by the other cross product, A times D. So that's 120, the B cell, times 50, the C cell, divided by 500, the A cell, times 80, the D cell, which works out to exactly 0.15. Yeah, so this is just a mathematical trick to do this more quicker and with a bit more precision. Only use it once we really understand what the odds ratio actually means. But yeah, once you do that, then this can really make your life a bit easier if you want to quickly calculate odds ratios. Okay, that was a lot. I think just about enough for this video lecture. I'll be seeing you Friday in the Zoom sessions. Take care, bye bye.